Good afternoon, everyone, and welcome. Now, today's webinar is coming to you from Environment One Utility Systems, and the focus is going to be on the 12 steps toward maximum hydrogen safety. First, I'd like to give you a little bit of background on our presenter today. Steve Kilmartin is Director of Products and Markets for Environment One's Utility Systems business. Considered a leading expert in the field of generator monitoring and maintenance, he has authored numerous papers, including work as Principal Investigator for the EPRI Turbine Generator Auxiliary Systems Volume 3, Generator Hydrogen System Maintenance Guide. Mr. Kilmartin began his career with E1 in 1988 as an instrument specialist. Prior to that, he worked in the instrument shop at GE and also as an applications engineer at Mechanical Technology Incorporated in New York. His career has taken him and around large machines and, of course, around the world for more than 30 years. Following the presentation, we will be taking your questions. Now, if you would like to submit a question, just look to the right of the Go to Meeting screen and you will see a section for the questions. So let's get started. It is my pleasure to introduce you to Environment One's Mr. Steve Kilmartin.
Thank you, Peggy. As Peggy mentioned, I will be presenting on hydrogen safety. Before I start, I'd like to note a study conducted by the U.S. Department of Labor that states the average age of workers in the energy industry is now over 50, and the industry estimates that up to half of its current workforce, more than 500,000 workers, will retire within the next 5 to 10 years. That study was conducted 7 years ago. What this means is the energy industry has lost or will be losing a large number of its skilled workforce, and these employees need to be replaced. Everything in this presentation is about safety, efficiency, and risk mitigation. This presentation was created for people with little or no experience with the hydrogen auxiliary system. It may serve as a refresher for experienced power plant personnel. However, I'm hoping it will provide new information for power plant employees entering into this field. For those of you that have sat through my previous webinars, the next couple of slides will be a review. We will talk about hydrogen as a cooling medium. We'll talk about the importance of purity monitoring. We'll talk about degassing and gassing the generator or purging the generator. And we'll also talk about the importance of monitoring dew point. In the late 1930s, there was an increasing demand to get more megawatts out of power generators. With generators, more megawatts means more iron. They get physically larger and generate more heat. In order to satisfy the demand for power without increasing the physical size of the generator, a different method of cooling was required. Imagine using a very explosive gas like hydrogen to cool a large machine that has components that are spinning at a very rapid speed. I find it very interesting that someone decided it would be a good idea to cool a generator with hydrogen. However, the idea worked, and now all large generators are cooled with hydrogen or a combination of water and hydrogen. Why hydrogen? Because it takes less horsepower to produce more power. Hydrogen has less windage and frictional losses. The relative density of hydrogen is 4 times less than air. What this means is that you can spin the rotor in the generator a lot easier when it's surrounded by hydrogen versus air. Hydrogen has better heat transfer characteristics. Hydrogen is 14 times more efficient at removing heat from components in the generator that are heating up. The bottom line is you get more megawatts per pound of iron by using hydrogen as a cooling medium. This chart supports the density and specific heat transfer characteristics discussed in the previous slide. Again, hydrogen at 45 psig is 4 times less dense than air and has a specific heat capacity 14 times greater than air. Again, meaning that you can spin the generator a lot easier and you're much more effective in removing heat from components using hydrogen versus air. There are additional benefits in using hydrogen as a cooling gas. Because it's a sealed environment, the generator has less chance of contaminants entering into it, such as water, dirt, or sand. Because it's a pressurized vessel, it suppresses partial discharge and also increases the level of voltage required to break down components. Hydrogen is not an oxidizing agent like oxygen is, and pure hydrogen will not support combustion. One of the problems with using hydrogen is you have to keep it in the generator case, and because hydrogen molecules are so small, they are hard to contain. This slide indicates a sectioned view of a hydrogen-cooled generator. The stator core is mounted inside the generator case, which serves as a pressure vessel which contains the hydrogen. One of the areas that is very difficult to seal the hydrogen, or the area where it's difficult to seal the hydrogen in the generator, is the rotating field or the rotor. You can see the hydrogen seals on each end of this generator. They're used to keep the hydrogen from leaking out. You will also note that the hydrogen fans on each end of this generator rotor, which is used to circulate the hydrogen. Some generators have 2 fans. Some have 1 fan. Some will have a blower assembly at the end of the rotor. These fans or blowers will create a high pressure and low pressure, which we will discuss later. This is a sectioned view of a hydrogen seal. Oil is used to seal the hydrogen in the generator and keep air from entering into the hydrogen. You can see from the top and the bottom of this slide where the seal oil is fed to the rotor shaft at 95 psig. This is a higher pressure than the hydrogen case pressure, which is 90 psig. So the hydrogen will flow in the direction of, or the seal oil will flow in the direction of the hydrogen and also in the direction of the air, creating an effective seal, keeping hydrogen in the case and keeping air out of the generator. This is what happens when you don't keep hydrogen inside the generator. I don't know the specifics of this failure. I do know that the seals broke down. There was a seal oil fire. There was also a hydrogen fire. The hydrogen actually caused the exciter cabinet to be blown off its frame. This is what you don't want to see the next morning coming into work. You can see where hydrogen escaped out of this generator, went into the exciter or collector cab, blew the exciter or collector cab from its frame. This was a total, this generator was totaled and could not be put back together. Why do we measure the gas purity? I believe the #1 reason is safety. Hydrogen has a very explosive range. Between 4 to 75% of hydrogen when mixed with air is explosive. The most explosive range is around 13% hydrogen in air. We also monitor the hydrogen purity for efficiency. the purer the hydrogen in the generator, the less windage losses you have, the easier you can spin the rotor, the more megawatts you can produce. So we're measuring hydrogen purity for both safety and efficiency. You also want to measure the gas purities during the degassing and gassing of the generator, as well as during normal operation of the generator. Risk mitigation could also be added to this list. If you have low purity, you can have problems within the generator. Someone might ask, well, what is a good hydrogen purity? You want the hydrogen as pure as possible. Typical purity will be better than 96%, sometimes ranging in the area of 98%. This slide lists some of the technologies used to measure purity. A manometer, which in the old days was a glass U-tube filled with mercury, which was used to measure the differential pressure across the rotor fan. And then by using a graph that was supplied by the OEM, you could convert this differential pressure to purity. A gas density blower, which also measures differential pressure, and the differential pressure again is converted to gas purity. The most frequently used technology today are thermal conductivity analyzers. There are different types of thermal conductivity analyzers on the market. They all use a thermistor as a sensing device. However, the thermistors, the measuring scheme, and the electronics can vary considerably between these analyzers. A newer type technology that has been introduced is a vibrating element. It is important that your analyzer is a triple range analyzer that can determine not only hydrogen and air during normal operation, but also hydrogen and CO2 and air and CO2 during the gassing and degassing process of the generator. It is also very important that these systems, since they are analyzing hydrogen and you're bringing hydrogen to the sensor cells, be rated to be used in a hazardous area, and that proper piping practices be followed to minimize oil contamination. Oil will affect the operation of all of these different technologies. These are some considerations to consider when speccing out an analyzer. Certainly you want the analyzer to be accurate. I believe as important, you want it to be stable. You don't want to keep calibrating this piece of equipment. You'd like to have a piece of equipment that would go a minimum of 6 months without having to be recalibrated. You want the ranges to be such that they'll cover all of your applications. So you want to be able to measure in the area of 70 to 100% hydrogen in air, and you want to be able to do 100 or 0 to 100% with hydrogen and CO2 and air and CO2. I also recommend you use redundant analyzers for two reasons. One, that you'll have a 2 out of 2 voting, but I also, in the event that one analyzer fails, you have another one as a backup. The sampling location and position of the analyzer is very important. As I mentioned before, you want to minimize the chance of oil getting into these units. You want to be able to filter out any moisture or oil that's in the line, and you want to make sure that you're getting a sufficient flow of hydrogen so that you're getting a representative sample. I mentioned earlier about the area classification. These, because they're bringing hydrogen to the sensor, the area that they're used in becomes a hazardous location. So you want this equipment certified to be used in those hazardous locations. Different countries have different requirements. In the U.S., it's a North American Electric Code, Class 1, Division 2, Group B. In Europe, it's ATEX. Then other countries have different requirements. Because of recent events in the U.S., I'd like to spend a little time discussing purging a generator or degassing or gassing a generator. When proper operating procedures are followed and the operating is performed by experienced plant personnel, there will be no issues. However, this is not always the case, especially with us getting a younger workforce at power plants. You need updated and understood standard operating procedures. This is critical. The first two items are critical. You should have a current P&ID. Over years, the piping systems get changed, instrumentation gets added, valving gets changed. You need to make sure that your P&ID is current. You need to verify that the valves are properly labeled and agree with the P&ID. You need to verify that your gas analyzer, and whether you're using 1 or 2, is calibrated and operating properly. If you are not using redundant gas analyzers, I would recommend the use of a portable gas analyzer during the purging process as a redundant analyzer. The next two items are very important because the valves on these gas manifolds are not exercised that often. In many cases, generators can go 5-10 years without being purged. So these valves are not being used, and the packing in the valves may become stiff or brittle, and when they are used, they might leak. So I think it's very important that you have a portable hydrogen sniffer available during the purging process. If you do not have this, at a minimum, I believe you should have a liquid leak detector, snoop or soap, available to look for leaks. You also want to make sure that you have a sufficient amount of carbon dioxide available, not only to purge the generator that you're working on, but also to purge all the generators that are on site. Because emergencies can occur where you want to purge those generators, and you want to make sure that you have a sufficient amount of carbon dioxide to purge them. I like the idea of creating signage to put in key areas to note what gas is in the generator. Obviously, during the normal operation, you got hydrogen in the generator, but during the purging process, it's possible that you either have CO2 or air in the generator. So this signage can be placed at the gas manifold, at the hydrogen purity analyzer, and also up in the control room. I like the idea of lockout for all the air in hydrogen supply systems so that you minimize the chance of air and hydrogen being put in the generator at the same time. I also like the idea of 2 people purging the generator. And ideally, these people, one person would come from operations and the other person would come from the I&C department. This is a sectioned view of a hydrogen-cooled generator, and the reason I put this up there just to show you where the carbon dioxide enters the generator and where the hydrogen enters the generator. During my presentation, I will use carbon dioxide as a purge gas. There are industries and utilities that recommend different gases. However, for my presentation, I'm going to use carbon dioxide. The carbon dioxide is fed through the bottom header of the generator. Because carbon dioxide is a heavier gas, it will force the hydrogen out the top of the header or air out the top header. So the hydrogen and air will come in through the top header. And then over to the left-hand side, there's 2 points where the analyzer takes its sample. Now that's during normal operation. And it's very important to note that you take a sample of hydrogen during normal operation across the fan of the generator, But during the purging process, you're going to be taking your sample at the vent line, which I'm going to show in a couple slides. This is a typical P&ID for the hydrogen auxiliary system. And I'm going to spend a few minutes talking about the various components in this system. On the top right-hand side, you can see where the supply CO2, hydrogen, and air is fed into the generator. Off to the left-hand side, we've got a pressure indicator for the CO2 supply pressure. We have a pressure transmitter that will send a signal up to control room. We also have a pressure indicator for the hydrogen supply and a transmitter that will feed the signal up to the control room. There are pressure relief valves as you come down the lines on the H2 supply and the CO2 supply. Very important, and I lost my pointer, so I can't point this out, but up in the upper right-hand corner, there's a H2 air spool piece. And this is a removable piece that will not allow you to put hydrogen and air in the generator at the same time. This is not foolproof. This does not eliminate the chance, but it minimizes the chance. And I'll point this out in the next slide. As you go down the hydrogen line, you can see that we have a pressure control valve. This is used to maintain pressure in the generator. This is either an automatic operation if IV 17 and 18 are open, or it can be a manual operation when 17 and 18 closed and 19 open. And then as you get down, there's two three-way valves that are used to put hydrogen and CO2 into the generator and air into the generator. Off on the left-hand side, you can see the 2 points where you're connecting the analyzer across the generator fan pressure and the generator fan suction. You also have a differential pressure indicator and transmitter that is across these 2 points. Transmitter again sending the signal back to the control room, the indicator giving you a local indication. You also have a point that's connected to the generator case so that you can monitor the case pressure and also again send the signal back to the control room with a transmitter. And then as you follow the line down, you can see a flow meter, FM1, and then the purity analyzer. Under normal operation, the flow will come in through the fan pressure, go up through the analyzer, and then return to the fan suction. Now, if the generator is offline and you don't have a differential pressure, DV2 is opened and goes to vent, and that is used to create a small flow through the analyzer so that you can monitor the hydrogen purity even when you're on turning gear of the generator. And another important note here is that and this line is at the bottom of the page. It's called a cal purge, the three-way valve. When we're purging the generator, that three-way valve is changed so that the line that's feeding the analyzer is coming from the vent of the manifold, so that we're monitoring the gas that's leaving the generator, not taking a sample from the fan differential pressure or suction lines. This is a picture of the cabinet that houses the components shown in the previous P&ID. Again, the two lower gauges are the CO2 supply pressure and H2 supply pressure. Behind those are the transmitters that monitor those two and send a signal to control room. The two upper gauges, one is a fan differential pressure gauge, and the other one is a case pressure. The little door on the upper right hand is the door to the analyzer. The purity analyzer is behind that door. And then you can see the spool piece, that little U piece that's in the piping. And that's a removable part that allows you to put either hydrogen in the machine or air in the machine, but it will now allow you to put both in at the same time. Again, this is not foolproof. It is still possible to put hydrogen and air in that generator by switching that. So it's very important that you know what gas is in that generator. This is a picture of a portable gas analyzer, which again I recommend the use of as a redundant analyzer during the purging process. This analyzer is not rated for a hazardous area, and it's designed to be used in a well-ventilated, safe area. Now I'm going to go through the purging process of the generator, and we'll make an assumption here that this generator was just worked on and it's got air in it, and now we want to put hydrogen in it. The key point here being that you don't want to put hydrogen in the generator while air is in there. So we want to put an inert gas to get rid of the air. So the first step that we're going to do is we're going to pressurize the generator. So I'm going to connect my air supply over on the right-hand side, lower right-hand side. I got the valves open so that I can put air in the generator. Now I'm putting air in the generator. This is going to come in through the let me see, this one is now coming through the CO2 header, the bottom header. And when the generator is filled with air and pressurized, we close off all the valves to run our air test. Now over on the left-hand side where you can see where the analyzer connects, that also is where the case pressure gauge is connected also. So one of those valves may be open during this point to monitor the pressure in the generator, the air pressure in the generator during this test. Once the unit has passed, once not only the generator has passed the air test, but the gas manifold has passed the air test also, now we want to put CO2 into the generator. So what I'm going to do is we're going to disconnect the air supply on the right-hand side, and we're going to connect the hydrogen supply and the CO2 supply. This is done with that spool piece that I mentioned. So now we're going to bring CO2 into the generator. The CO2 is going to come up on the bottom header. CO2 being heavier than air is going to force the air out of the top header and go out to vent. Now you'll note that while we're doing this, we're analyzing our gas on the right-hand side, the analyzer purge connection, and that's where we're taking our purge sample. And you'll also note that if I was monitoring my gas purity from my analyzer during normal operation, as soon as I started to put CO2 in that generator, that's what I would see, because they were taking the sample from the bottom of the generator. From taking it at the point of the vent, the generator has to be filled with CO2 before this analyzer recognizes that I got pure CO2 in the generator. That's a very important point. Now that I have CO2 in the generator, an inert gas, it's safe to put hydrogen into the generator. So I'm going to now connect my hydrogen line, or disconnect my CO2 line, and start opening the valves for my hydrogen feed. The hydrogen is going to come in through the top header. The hydrogen being a light gas is going to go into the top header, and it's going to force the heavier CO2 out the bottom header. And again, you can note that the analyzer on the analyzer purge connection is not going to see hydrogen until the generator is filled with hydrogen. Now that the generator has been filled with hydrogen, I can go into my normal operation, opening the valves to the analyzer. The fan's now turning. I got a differential pressure that's going to create a flow through my gas analyzer. You'll note that the hydrogen supply is still tied to the generator, and there will be a regulating valve there that will keep that generator pressure at a predetermined point, typically 30 or 60 psig. I'm not going to go through the CO2 fill or the air fill, which is a degassing process. This is just a reverse of what we did previously. Now I'm going to talk about the dew point, measuring dew point. Why do we measure dew point? The main reason is to prevent component failure and insulation failure and risk mitigation. Whether dew point affects efficiency is often debated, and I will show a slide later in this presentation that supports the fact that dew point has very little effect on efficiency. I don't think there are any safety issues related to having high dew point, although if a retaining ring lets go, I guess you could have a safety issue. What is good dew point? 0 is usually the alarm point that most OEMs recommend. So you want the dew point to be lower than 0. Hydrogen from bottles or bulk systems is usually very dry. However, it is possible to get a bottle of wet hydrogen. It's rare, but it can happen. Hydrogen produced by hydrogen generators is always dry. So where does the moisture come from? In most cases, the seal oil or the cooling water, or if your generator stator is cooled with water, it could come from the stator cooling water. High dew point can support insulation failure or electrical tracking. There's a great paper that's written by Generator Tech, who is a manufacturer of flux probes, that discusses insulation failure in detail. And I believe this paper is available on their website. Again, the name of the company is Generator Tech. High dew point can support corrosion. Some early retaining rings that were made of 18.5 stainless, the 18.5 stainless was susceptible to corrosion, which would, as a result of high dew point. With base load generators, you have a constantly warm temperature in the generator, so condensation really doesn't form in these units. However, with peaking units, where you're cycling the generator, this can result in temperature fluctuations, which can result in condensation forming in the generator. This slide shows a retaining ring failure. The retaining ring are the most highly stressed mechanical components in the generator. And you need to make sure that the integrity of these rings is maintained. As I mentioned, some earlier retaining rings, again, were made of an 18.5 stainless steel, which could get corrosion cracks as a result of moisture or high dew point. You certainly don't want this to happen to your generator. This is an example of insulation failure in the turns of a rotor. Moisture, along with other contaminants, can form a conductive bridge, which can lead to electrical tracking or cause the insulation to deteriorate, causing a coil-to-coil short. As I mentioned earlier, there's a great paper that's written by the late Don Albright, founder of Generator Tech, that discusses insulation failure in detail. This is a chart I mentioned earlier that supports the fact that a change in dew point has little effect in the density, which would mean that it has little effect in the efficiency of the generator. You can see from this slide, and by the way, this slide was created by NASA, that a change of going from plus 15 degrees C to minus 15 degrees C has very little effect on the gas density, meaning a 30-degree swing in dew point will have little effect on the generator insulation. However, you can see that purity has a major effect on the density. Where does moisture come from? There are some installations where turbine lube oil and hydrogen seal oil are from the same source. They share the oil source. In this situation, steam from the turbine will force moisture into the oil. And then when that oil, if that oil is not properly treated and the vacuum pumps aren't operating properly, that moisture in the oil will be absorbed by the hydrogen in the generator. The hydrogen will actually act as a sponge and pull the moisture from the oil. It is also possible to get a bottle of hydrogen that is not as dry as it should be, as I mentioned earlier. Thermal cycling, it will not create moisture. However, condensation can form as a result of components heating and cooling. And as I mentioned earlier, if the generator has the stator cooling water system, you can have clip leads, you can have leaks in the Teflon tubing, so you can have water get into the generator from the stator cooling water system. Here are some methods, sensors or technologies that are used to monitor dew point. There's a ceramic chip type sensor, there's a silicon based sensor, aluminum oxide sensor. I don't believe that chilled mirrors have ever been used to monitor dew point in hydrogen cooled generators. The three sensors that are listed above are measuring a change in the electrical properties, whether that change be a change in capacitance, change in resistance, or a change in impedance. Here are some considerations, some of them the same as when you're purchasing or speccing out a hydrogen analyzer or gas analyzer. You want it to be accurate, obviously. Again, you want it to be stable. You don't want to have to recalibrate this piece of equipment all the time. You want to make sure that the pressure is being compensated for, because a change in pressure will affect the dew point reading. You want to make sure that the monitor covers the range that you're looking for. As I mentioned earlier, a good dew point is 0. So you want to make sure that, or the alarm point is 0. You want to make sure that your hydrogen dew point is lower than 0. So a good range may be plus 40 degrees to negative 60 degrees. You want to make sure that the effects of temperature and pressure have little effect on the reading of the dew point sensor. You want to make sure that the sample location is good. Again, you don't want oil in this sensor, so you want to make sure you follow proper piping practices to keep oil out of the sensor. Oil will cause the sensor to fail. You want to filter out oil, but you don't want to filter out moisture. So it's important that your filter that you're speccing meets your needs. You want to make sure that you're getting a good hydrogen flow so that you're getting a representative sample of that hydrogen. Again, because you're bringing hydrogen to this sensor, that area becomes a hazardous location. And you want to make sure that at a minimum, the sensor is rated to be used in a hazardous area. And if that's the case, you want to make sure that the sensor is rated for a hazardous area and the electronics are in a safe area. I recommend, however, that the sensor and electronics be rated to be used in a hazardous area. Again, in the U.S., the requirement is the North American Electric Code, Class 1, Division 2, Group B. Europe is ATEX. Australia and South Korea is IECEX. So different countries have different requirements. In closing, we know that hydrogen is a very effective cooling gas. By using hydrogen as a cooling medium, you can get more megawatts without increasing the physical size of the generator. Again, more megawatts per pound of iron. Recent catastrophic events have reinforced the critical importance of safety and risk mitigation strategies in power plants worldwide. You need to have good documentation. It's extremely important that your documents be current and up to date. You should have well-written test procedures for all of your instrumentation. If you don't have well-written procedures, you should either create them or talk to other plants that might have some. Or also contact the manufacturer. The manufacturer of this instrumentation may have written test procedures that you can use. You should have a documented training program for all your new employees. Again, if you don't, talk to other plants. Talk to manufacturers of the equipment. They often have training programs. In the past, when we had apprentice programs at power plants, people were hired and they would spend time with more experienced people, sometimes for up to years, gaining experience on equipment. That may not be the case nowadays. So it's very important that you have well-written test procedures and a good training program. All of your monitoring equipment should be tested and calibrated. You should maintain a calibration schedule for your monitoring equipment. I failed to mention this, but with dew point analyzers, the sensors on dew point analyzers need to be recalibrated on a yearly basis. And the unfortunate thing with them is that you can't order one for a sensor for a spare, because they begin to age as soon as they're calibrated. So the sensor itself needs to be calibrated every year and used when you get it. You should have proper tools and safety devices. When you're working in a hazardous area, you should have equipment and tools that are suitable. In an area that you're dealing with hydrogen, the tools should be non-sparking. And the people that are working in this area should be carrying personal gas detectors. It is critical, again I state this, it is critical that you have well-written, up-to-date, standard operating procedures and a current P&ID for your hydrogen system. As I said at the beginning of this presentation, it's all about safety, increased efficiency, and risk mitigation. Thank you.
Thank you very much, Steve Kilmartin. Very interesting stuff. And Steve, we do have some questions coming in.
Okay.
The first question, considering the increasing restrictions and monitoring of CO2 on the atmosphere, is there any reason why another inert gas, say, such as maybe nitrogen, can't be used instead of the CO2?
No. As a matter of fact, European utilities, I believe, are setting the trend in this case. There are power plants that will use argon, and there are plants that will use nitrogen. CO2 is a greenhouse gas, and that is a concern. The nice thing about CO2 is it's much heavier than the other gases, and so you create a blanket between the CO2 and the hydrogen, or the CO2 in the air, during the gassing process. However, argon or nitrogen can be used as a purging gas in place of CO2.
Okay, we have another question. When a generator is purged, is any of the hydrogen that was in the generator captured, so perhaps it can be reused at another time?
I'm not aware of that taking place. I am aware of a company, and it's a startup company, and this is a brand new technology. However, they're making a device to recapture the hydrogen and store the hydrogen, so that when the work is done on the generator, it can be reused and put back into the generator. I don't have that information off the top of my head. However, if someone is interested in it, I could put them in touch with this company.
Okay, speaking of emergency evacuation in the event of a shaft sealing failure, how would your emergency evacuation, how would you be able to do that without putting people at risk, because the valving is typically right underneath the generator?
Boy, that's an excellent question, and we've been running into that situation or a requirement that will allow you to emergency not purge the generator, but emergency depressurize the generator from the control room. So what you are doing is you're putting a solenoid valve down in the manifold on the CO2 supply line, and you're putting a solenoid valve on the vent line of the generator, so that in the event that, let's say, a seal fails, you can depressurize that generator by shutting off the hydrogen supply and opening the case to vent. Now, some utilities, there's Eskom in South Africa, for instance, is actually not only depressurizing the generator, but they are also degassing the generator. So the first step is to release the hydrogen pressure, and then the second step is to fill that generator with CO2. And again, this is done by solenoid valves, and it is done from the control room. It is not done from down traditionally where the generator gas manifold is located down underneath the belly of the generator. So to answer your question, to depressurize the generator, solenoids can be added to the hydrogen supply and to the hydrogen vent, so that one can be open, one can be closed, and the generator can be depressurized.
Steve, just for clarification, when you were mentioning the 0 degrees as a typical target for dew point, were you referencing Fahrenheit or Celsius?
I was mentioning Celsius. And most generator manufacturers will use that as their alarm point, so that if the dew point goes above 0 degrees Celsius, then some action should be taken. So the recommendation is that you keep your dew point lower than 0 degrees Celsius.
Okay, the next question is actually a two-part question. What is E1 doing about writing a procedure with a checklist for both isolation to perform instrument maintenance, the calibration and cleaning, and again for releasing from the maintenance activity?
I'm not sure if I understand that completely. If they're asking what we do or what we are writing to isolate our equipment or to isolate the generator. Could you ask me the question one more time?
Absolutely, and I'll give you the second part of the question as well. It says, what is E1 doing about writing a procedure with a checklist for both isolating to perform instrument maintenance and then again for releasing from the maintenance activity? The second part would be, what will the technician confirm before requesting valve lineup and logic forcing to be returned to normal operating condition?
Okay, let me answer that, I guess, in two parts, as the question was asked in two parts. Environment 1 has what is called an operating philosophy. It's a general document that power plants can look at to give them ideas. We have to be very careful about telling a power plant how they should be maintaining or operating their generator. So this operating philosophy is general, and it gives E1's point of view of how your equipment should be operated, how you should isolate it, how you should maintain it. However, we recommend that power plants write their own procedure. We'll support it, but we recommend that power plants write their own standard operating procedure. And as I mentioned in my PowerPoint presentation, if they don't have good standard operating procedure, I've found that utilities are very willing to share information, and that if you contact another utility or several utilities, I'm certain that they would share their standard operating procedures with you. Now, could you repeat that second question one more time?
Yes, the second part of the question, what will the technician confirm before requesting valve lineup and logic forcing to be returned to normal operating conditions?
Okay. Again, this is getting back to the two critical pieces of information that I recommended, and the one being that you have a well-written standard operating procedure, and also that you have a current P&ID. And as I said, I recommend that there two people are part of the purging process, so that one can read the standard operating procedure while the other one is following along on the P&ID and closing and opening the valves that are necessary in order to purge the generator. So key points again, or what would be the checkoff? The checkoff would be part of the standard operating procedure. And that, again, while one person's reading it, another person's looking at the P&ID and controlling the valves, so that you got two sets of eyes looking at the instruments while you're doing this process.
Okay. What is the relative risk involved in purging versus normal operation?
During normal operation, it's very difficult to put air in the generator. So you've got the generator filled with air. Pure hydrogen will not support combustion, so you're minimizing the risk or the safety risk. Now, that's not to say that you can't put air into it, but there's less of a chance. Where the hazard increases is during the purging process, where you run into a chance of putting air in the generator at the same time that's hydrogen in there, or vice versa. And there have been cases recently where this has taken place, where either hydrogen was put in the generator or wasn't fully purged and they put air in it, or there was air in the generator and it wasn't fully purged and they put hydrogen in the machine.
Okay, we have a request from one of our listeners today. It says he has clients who perform inspections on their generators every 2 years. How can they manage calibration of the dew point monitor if it's supposed to be done annually?
Well, these cells can be changed while the units are online. I guess it's not difficult. It's just an inconvenience that these cells have to be changed out on an annual basis. Now, we have experienced cells that have gone longer and have operated longer than year period if the depending on the period or depending on the dew point of the hydrogen. Surprisingly, if the hydrogen is more wet, the sensors will last longer. But the program that we have is that on an annual basis, we will get a new sensor and replace the existing sensor, and again, you can do that online, and then take that existing sensor and we'll have that recalibrated. So it's an exchange program.
All right. How actually do you calibrate a dew point sensor?
I unfortunately, I can't answer that question. I have no idea.
Okay, well, then there was, what is the highest purity that can be achieved where you can see significant efficiency gains?
I have a graph, and I didn't have it in this presentation, but I have a graph that has older information in it. But it shows that if you go in the neighborhood from 92 to 98, that there is a sufficient change in the windage loss in the generator, and I believe it's in kilowatts, how the dollars to generate a kilowatt, and how much that changes. And I'd be happy to share that chart with anyone. But if you go 1 or 2%, the efficiencies on a smaller generator in the neighborhood of 200, 300 megawatt might not be that major. But if you go 1 or 2, or if you go 2% on a large nuclear unit, that may be significant. But I have a chart that shows that if you go from 4 to 8, it's quite a change.
Okay, and it looks like we have one final question here. Typically, what is the cost of hydrogen-cooled generator failure, and how is that different from an air-cooled failure?
Generator failures, a generator can fail for many reasons. And for instance, and I am not a generator expert, but I've sat in a lot of conferences and a lot of papers, so I hear about these problems. And if, for instance, you have a bushing problem, it would be a lot less money to repair that bushing than if you had a stator core that had to be restacked or partially stacked. So I don't suspect that between, let's say, a 200 megawatt air-cooled generator and a 200 megawatt hydrogen-cooled generator, and again, I'm not an expert in this, but I don't suspect there's a major difference in cost between, for instance, restacking a core or rewinding a core or rewinding a rotor or changing the retaining rings on a rotor, whether it's an air-cooled or hydrogen-cooled. I don't suspect that there's much difference in cost. However, again, I have to say that I'm not an expert in this field.
Well, we want to say thank you very, very much to Steve Kilmartin today. Steve is the Director of Products and Markets for Environment One's Utility Systems. Thank you so much, Steve, for all the great information. Thank all of you all for joining us today. This does conclude today's webinar, and we hope everyone goes out and has a wonderful day.
Thank you.